In 2018, the Planck satellite measured the curvature of the universe and returned a number. Omega K equals 0.0007 plus or minus 0.0019, the most precise geometric measurement in the history of science. And what it said was this: the universe is flat. Not approximately flat, not flat enough. Flat to within 0.2%, sitting so close to the exact value of zero that every instrument we have built cannot push it off that mark. Most people heard that and nodded. Flat, fine, it's a shape, move on. But here is what flat actually means, stated without softening. A flat universe is not large. It is not vast. It is not boundless in the way we use that word when we want to gesture at something very, very big. A flat universe is mathematically infinite. It extends without limit in every direction. That is not a metaphor borrowed from philosophy. It is the logical consequence of a single number equaling zero. When general relativity processes a curvature of exactly zero, the answer it produces for the total size of the universe is not a large finite number. It is no finite number at all. The geometry simply does not stop. That is what the Planck data forced into existence in 2018. Not a discovery that the universe is large, a mathematical obligation that it has no boundary. And here is where the provocation bites. We cannot see it. Everything we have ever photographed, measured, mapped, or detected sits inside a sphere roughly 93 billion light-years across. We call that sphere the observable universe. It has a precise diameter derived from the same lambda CDM model the Planck satellite confirmed. It contains approximately 2 trillion galaxies. It holds every supernova we have ever timed, every CMB photon we have ever caught, every object we have ever resolved, through any lens, on any instrument, on any spacecraft. And it represents, under the geometry the data demands, a finite region inside something that goes on without limit. The observable universe is not the universe. It is a window. Every map humanity has ever drawn of the large-scale structure of reality, every catalogue, every survey, every chart of the cosmic web covers only that window. What exists beyond it is not on any map. Not because no one has looked, because looking requires light, and the light from beyond that boundary has not had time to reach us. This is the critical distinction, and it is easy to miss. The horizon above our heads is not the edge of space. Space does not end there. The horizon is the edge of time, the boundary set by the age of the universe itself. The universe is 13.8 billion years old. Light travels at a fixed speed. The observable sphere is, at its most basic, the region from which light has had time to reach us since the Big Bang. Beyond that sphere, the universe continues. It has been continuing all along. We simply have no light from it yet, and depending on how the geometry works, we may never. There is a second thing the Planck result exposed, quieter but equally precise. Earth sits at the centre of that 9.3 billion light-year sphere, not because Earth is special, not because our galaxy occupies a privileged position, but because that is where our instruments are. The centre of the observable universe is always the observer. An astronomer on a planet orbiting a star in the Virgo cluster would see herself at the centre of her own sphere, the same size, surrounded by her own horizon. A civilization in a galaxy a billion light years from here would see the same thing. The horizon is not a feature of space. It is a feature of the relationship between the speed of light and the age of the universe. And it follows every observer everywhere, which means every civilization that has ever existed or ever will looks out from the center of a bubble and sees a universe that appears to have them at its heart. None of them are at the heart. The heart doesn't exist. There is only the bubble, and beyond the bubble, more universe different for every observer, but equally finite in reach, equally bounded by the same physics of light and time. Before 2018, a scientist could have reasonably asked whether the universe is infinite and held the question at arm's length. The geometry wasn't constrained tightly enough to force an answer. But the Planck final data release closed that distance. Omega k equals 0.0007 plus or minus 0.0019. If the universe carries any curvature at all, it is smaller than our best instruments can resolve. And the value that sits inside that uncertainty band, the value the data crowds closest to, is zero. Zero curvature. Infinite universe. So when that number came back from the Planck satellite, it did not settle the question of what lies beyond the horizon. It made that question mandatory. It converted a philosophical curiosity into an arithmetic consequence. If the universe is infinite, and the geometry says it is, within the precision of every measurement ever made, then something exists beyond our horizon. The question is not whether, the question is what. And the answer physics gives when you press it is not reassuring. Not alien, not void, not silence, something far stranger than any of those. What that is, and why the math forces it on us whether we want it or not, that is what this is about. The observable universe is a sphere. Its diameter, derived from the lambda CDM model confirmed by the Planck 2018 data release, is approximately 93 billion light-years. Written in meters, that is 8.8 times 10 to the power of 26, a number so removed from human scale that the only honest thing to do is stop pretending. Comparison helps. No analogy involving grains of sand or drops of water closes that distance. The observable universe is not large the way a mountain is large or the way a continent is large. It is large in a way that severs the intuition entirely and leaves only arithmetic. Inside that sphere, roughly 2 trillion galaxies, each galaxy containing, on average, hundreds of billions of stars. Each of those stars potentially orbited by planets. All of it, every object, every photon, every gravitational wave ever detected, contained within a bubble whose wall is not made of matter but of time. That is the key fact, and it is worth sitting with for exactly one moment before moving forward. The wall of the observable universe is not a physical surface. Nothing is there. No boundary marker, no change in the density of space, no place where matter stops. The wall is a temporal limit, the point beyond which light has simply not had enough time to reach us. The universe is 13.8 billion years old. Light travels at 299,792 kilometers per second. Multiply one by the other and you get the maximum distance any signal could have crossed since the Big Bang. That is where the bubble ends. Not in space, in time. But here is where the measurement becomes genuinely disorienting, and why the diameter of the observable universe is 93 billion light-years and not 27.6 billion, the number you might calculate by doubling 13.8 billion years of light travel. Space itself has been expanding throughout those 13.8 billion years. When light left a distant galaxy near the beginning of the universe, that galaxy was far closer to us than it is now. As the light travelled, the space between us and its source stretched. The photons kept moving forward at the speed of light, but the destination kept receding as the fabric of space expanded behind them. By the time those photons arrived, the galaxy that emitted them had been carried by cosmic expansion to a position far beyond where the light originated. The light travelled for 13.8 billion years, but the source is now 46 billion light-years away. This is not an error or a paradox. It is the direct consequence of living in an expanding universe. The farthest objects we can see are not 13.8 billion light-years away. They are 46 billion light-years away. The co-moving distance to the cosmic microwave background, the oldest light we can detect, is approximately 46 billion light-years in every direction. That is the true edge of the observable sphere, not where light ran out of time, but where the source of that light has been carried by 13.8 billion years of expansion. The cosmic microwave background itself deserves a specific account. It is not a distant galaxy. It is not a star or a cluster. It is light emitted when the universe was approximately 380,000 years old, the moment when the primordial plasma cooled enough for electrons and protons to combine into neutral hydrogen, and for the universe to become transparent for the first time. Before that moment, the universe was opaque. Light could not travel freely. Every photon we might detect from before 380,000 years after the Big Bang is simply gone absorbed, scattered, irretrievable. The CMB is the oldest electromagnetic signal the universe allows us to receive. It is the wall of the bubble, not because space ends there, but because physics prevented any light from escaping earlier than that moment. And then there is a second boundary, less discussed, but in some ways more consequential. The cosmic event horizon sits at approximately 16 to 17 billion light-years from Earth, not 46 billion, 16 to 17 billion. This is the distance beyond which any light emitted right now in this moment will never reach us. The expansion of space is already carrying those regions away faster than light can bridge the gap. A photon departing today from a source at 17 billion light-years will spend the rest of the universe's life running toward us and never arrive. The gap between us and that source will widen faster than light can close it. This means the observable universe and the reachable universe are not the same thing. We can still see objects that are 46 billion light-years away because their ancient light has already crossed that expanding void and landed on our instruments. But anything beyond 16 to 17 billion light-years right now is already sending signals we will never receive. The horizon for future information is smaller than the horizon for current observation. And it is shrinking. In 1999, Neil deGrasse Tyson was at the Hayden Planetarium when a 9-year-old girl asked him how there could be more universe past the part we can see, if the universe is everything. He knelt to her level. He told her, "We are inside a bubble. Bubbles have walls you cannot see through, but that does not mean the ocean stops there." The girl went home and stayed up for 3 nights, drawing bubbles inside bubbles. Her mother said she couldn't stop. That image is precise in a way that most technical descriptions are not. The wall is real, defined by physics, measured by satellites, confirmed to 4 decimal places, and the ocean is real. The universe beyond the CMB has been there since the beginning, carrying matter and structure and whatever physics permits. Unreachable not because of distance in any simple sense, but because of the hard arithmetic of light speed and cosmic age. We are inside, looking at a wall that is not a wall, knowing the ocean continues, unable to see a single wave of it. What lies beyond that wall is the question the geometry of the universe has now forced into mathematics. And the answer does not start with alien strangeness or beautiful emptiness. It starts somewhere far more unsettling, with the farthest single object any human instrument has ever resolved, a ghost from 300 million years after the Big Bang, whose light arrived in 2022 and whose source no longer exists in our universe at all. In the autumn of 2022, the James Webb Space Telescope was pointed at a patch of sky near the constellation Fornax, a region that appears to the naked eye as absolute nothing. No star, no smudge, not even the suggestion of light. The telescope stared for hours. And in the resulting image, buried in a field of older, closer galaxies already straining the limits of prior instruments, there was a red smear, faint, almost implausible. A signal so attenuated by distance and expansion that it had been shifted entirely out of the visible spectrum into infrared by the time it arrived. That smear was JADESGSZ130, the farthest object ever observed by any instrument in human history. Not approximately, not with any meaningful competition. A galaxy from the edge of what the universe permits us to see. The light that formed that image left its source when the universe was 300 million years old. 300 million years, a number that sounds large until you set it against 13.8 billion, and realize it represents roughly the first 2% of cosmic time. Stars had barely begun to form. The first galaxies were still assembling themselves out of primordial hydrogen, coalescing under gravity in a universe that had only recently cooled enough to permit structure of any kind. And somewhere in that early dark, this galaxy already existed, already burning, already emitting light that would travel for 13.5 billion years before hitting a mirror above the Earth's atmosphere. Dr. Emma Curtis Lake was the lead scientist on the discovery. She described what happened in the moment the data resolved. The light, she said, was beautiful. But that was not why she wept. She wept because she had realized something in the instant the measurement confirmed. That galaxy is already gone. The light we caught was a ghost. The real galaxy, the structure that emitted those photons 13.5 billion years ago, crossed the cosmic horizon long ago. It no longer exists within our observable universe. Whatever it became, whatever happened to the stars inside it, whether it merged with other galaxies, collapsed, dispersed, none of that information will ever reach us. The object we named and measured and called the farthest thing ever seen is, from the perspective of the present universe, unreachable, permanently. The observation was not a window into that galaxy's existence. It was a record of its departure. Curtis Lake put it in 4 words. We are archaeologists of the dead. That phrase deserves to sit for a moment, because it is not a metaphor. It is a description of the technical reality of every telescope ever built. When you observe a galaxy 2 billion light years away, you are seeing it as it was 2 billion years ago. When Hubble photographed the deep field, every object in that image was a historical document, not a live transmission. Astronomy has never, not once, shown us the universe as it currently is. It has only ever shown us the universe as it was, at various points in the past, the light from those moments finally completing its crossing and landing on our detectors. JADESGSZ130 simply makes this visible at its most extreme. At 13.5 billion years of light travel, the gap between observation and reality is total. There is no version of improved technology that closes it. No faster telescope, no better mirror, no future instrument resolves the problem, because the problem is not instrumental, it is physical. The expansion of space has already carried JADESGSZ130 beyond the event horizon. Light it emits today will never reach us. Light it emitted yesterday will never reach us. The channel is closed. What we observed in 2022 was the last message from a civilization address that no longer exists in our universe. And here is what that means for the condition we are already in, right now, not at some distant future point. The horizon is not something that will eventually begin erasing the sky. It has already been erasing it. JADESGSZ130 is not a warning about what comes next. It is evidence of what has already happened. Objects have already crossed. Signals have already been cut off. We have already named and studied things that we can never visit, never revisit, never confirm in their present state. The farthest galaxy we have ever seen is proof that observation and knowledge are not the same thing, that to see something at this scale is not to know it, but to receive a transmission that ended billions of years before anyone was alive to receive it. That distinction matters because it changes what we mean when we say we understand what lies beyond our horizon. Every inference we draw about the universe past the CMB wall, every extrapolation into the unobservable rests on light we have already caught, already archived, already interpreted, already aging. The data is not being refreshed. The photons that carry the oldest information have already arrived. What we call the frontier of cosmological knowledge is, in practice, a filing cabinet of ancient signals from sources that have long since moved beyond reach. Curtis Lake's word archaeologists implies something else too. Archaeology proceeds from fragments, the potsherd, the inscription, the buried foundation. It reconstructs what it cannot observe directly. It is disciplined inference from incomplete evidence. Every cosmologist working on the structure of the early universe is doing exactly this, inferring a present from a past, a whole from the fragment that survived the crossing. The difference is that an archaeologist can, in principle, dig deeper. A cosmologist working at the horizon cannot. The trench stops at 46 billion light years in every direction, and the soil below is permanently sealed. So when JADESGSZ130 was confirmed as the farthest object ever observed, the honest response was not triumph. It was the sensation Curtis Lake described, a recognition of irreversibility. We had seen the farthest thing we are physically capable of seeing from this position in space and time, and it was already gone. What does that say about the space beyond it? The galaxy sat close to the observable edge, a thin region where our ability to detect objects ends not because objects stop existing, but because the light from earlier than 380,000 years after the Big Bang was never emitted in a form we can receive. Past that boundary, the universe has been running continuously for 13.8 billion years, building structure, evolving, expanding, and not one photon from that activity prior to recombination can ever reach us. We can name the edge. We have even managed to touch it with a single detection. But what exists on the far side, and how much of it, and in what condition, remains a question the light itself refuses to answer. So the question stands: if the farthest thing we have ever seen is already gone, what does physics say about the space it came from? What exists in the dark beyond the filing cabinet's edge? The answer is not what you expect. It is not alien. It is not void. It is not even particularly dramatic at first. It is more of the same. That phrase carries more weight than it appears to. When cosmologists ask what lies beyond the observable horizon, the most conservative answer, the data supports the answer that requires no new physics, no exotic assumptions, no theory beyond what is already confirmed, is that the universe out there looks like the universe in here. More galaxies, more stars, more planetary systems, more hydrogen and helium bound by the same gravitational equations, more cosmic filaments and voids arrayed in the same web structure we have spent decades mapping on our side of the boundary. Not a different universe, not even a strange one, an extension of this one, following the same rules, building the same structures, running the same clock. This is called the cosmological principle. It is among the most tested assumptions in physics that the universe, on large enough scales, is statistically homogeneous and isotropic, the same in every direction, the same everywhere you look, with no special regions, no privileged locations, no center. On scales smaller than a few 100 million light years, the universe is lumpy, galaxies cluster, voids gape, filaments stretch between superclusters. But zoom out far enough and the lumpiness averages out. Every large patch of sky resembles every other large patch within the expected statistical variation. Every survey we have ever conducted supports this. The Sloan Digital Sky Survey mapped the positions of hundreds of millions of galaxies. The distribution, when smoothed to sufficient scale, is uniform. The CMB, that oldest detectable signal, is isotropic to 1 part in 100,000. The same temperature, the same spectrum in every direction. Tiny fluctuations, the seeds of all subsequent structure, but no gross asymmetry, no hemisphere that looks fundamentally different from another. If the cosmological principle holds beyond our horizon and there is no physical reason, it would suddenly stop at the boundary of what we can see. Then the universe out there is a statistical continuation of the universe in here. The bubble's ocean is not alien. It is more ocean. That thought takes a moment to register properly. Because when you stare at the JADESGSZ130 image and confront what lies past the detection limit, the natural assumption is that the beyond is qualitatively different, darker, emptier, governed by different rules, perhaps. What we cannot see feels as though it should be otherworldly. Instead, physics says there are galaxies out there too. Superclusters, filaments, voids. Stars burning through their hydrogen at the same rate. planetary systems orbiting with the same orbital mechanics, shock waves propagating through interstellar gas at the same speeds. The same physics that assembled everything we have ever photographed is still running out there in regions that will never send us a single photon, assembling the same results. And now comes the part that stops being comfortable. The observable universe contains roughly 10 to the 80 baryons, protons and neutrons, the ordinary matter that composes everything we have ever detected. That is a finite count, not a rough estimate, a number. And quantum mechanics constrains the number of physically distinct configurations that a given volume of space can hold. The quantum state of a system is described by a finite number of parameters: particle positions, momenta, spin states, and those parameters can take only discrete values at the smallest scales. This means that within any volume the size of our observable universe, the number of possible physical arrangements of matter is large but bounded. It does not go on forever. It is a big number, but it has a last digit. Here is the consequence of that arithmetic applied to an infinite universe. If the universe extends without limit, if space goes on forever in all directions, as a flat universe implies, then it contains an infinite number of regions, each the size of our observable sphere. An infinite number. And each of those regions is filled with one of a finite set of possible configurations. Infinity divided by any finite number is still infinity. But the number of configurations is not infinite, which means that every possible configuration must appear not once, not 1,000 times, but an infinite number of times. This is the pigeonhole principle applied at cosmic scale. If you have infinitely many pigeons and only finitely many holes, every hole gets infinitely many pigeons. The configurations are the holes. The regions of space are the pigeons. An infinite flat universe cannot avoid infinite repetition. Repetition is not a coincidence, it is not a curiosity, it is forced by the arithmetic. The universe beyond the horizon does not merely resemble ours. Somewhere out there it duplicates it. Not approximately. The configuration of every particle, every galaxy, every mote of dust in every interstellar cloud repeated. The same filing cabinet, refiled. The same map, redrawn. Not by design. By inevitability. This is still the conservative picture. No new particles have been invoked. No exotic fields. No separate physical laws. The only inputs are the universe is flat, supported to within 0.2% by Planck data. The universe is infinite, the logical consequence of flatness in a simply connected topology. And quantum mechanics limits the information density inside any finite volume. Those three premises alone, all of them already embedded in standard cosmology, force the conclusion that exact repetition is not an outside possibility, it is the default. Think back to Tyson's analogy, the bubble in the ocean. The ocean does not stop at the bubble's wall, it continues. And in a genuinely infinite ocean, the same arrangement of water molecules that forms the wave crest hitting a shoreline right now is forming somewhere else, in some distant patch of identical water at this same instant, because there are only so many ways the molecules can arrange, and infinite space to arrange them in. The wall is not the edge of the ocean, and the ocean is not alien. The question that emerges from this is not whether repetition happens. The math has already answered that. The question is what the word copy actually means when it is applied to a region of space identical to the observable universe and how far away that nearest copy sits. That distance has been calculated. It is a number so large it requires a different relationship with mathematics to hold in mind at all. And that is where we go next. The nearest identical copy of everything you can see, every galaxy, every star, every atom, arranged exactly as it is arranged right now, sits at a distance of 10 to the power of 10 to the power of 28 meters. Write that down. Try to picture it. You cannot. No one can. That is not a failure of imagination. It is a feature of the number. To understand what that distance actually is, consider that the observable universe itself spans roughly 8.8 times 10 to the 26th meters. The exponent in Tegmark's number is not 26. It is 10 to the 28th. The distance to the nearest copy is not 10 times larger than the observable universe, or 1 trillion times larger, or 1 trillion times larger. It is larger by a factor so extreme that the observable universe, used as a unit of measurement, would need to be multiplied by itself repeatedly, the iterations stacking up into a tower of exponents before you approach the scale of the gap. Every number you have ever worked with, every measurement science has ever made, lives somewhere between 0 and 10 to the 26th. Tegmark's number begins its meaningful content at 10 to 10 to the 28th. There is no analogy, there is no ladder of comparisons that gets you there. Tegmark himself was asked to describe it. He said, "That number is so large that if you tried to write it out in zeros, every zero smaller than an atom, you would fill the entire observable universe and still not finish." That is what infinity means. Not that it's possible, that it's forced on us by math. Not possible. Forced. That distinction carries everything. This is not a speculation. It is not a poetic extension of the data into territory where imagination runs loose. It is a calculation, executed under specific assumptions, a flat universe, an infinite spatial extent, quantum mechanics constraining the information density inside any finite volume, all of which are already embedded in the standard model of cosmology. Tegmark's paper, published in 2003 Inches, Scientific American, and developed further in the years since, derives the number from first principles. The assumptions may be wrong. The curvature measurement may eventually reveal a small positive value that closes the universe, which would change everything. But given what the Planck data currently shows flatness to within 0.2%, the calculation is not exotic. It follows. No new particles are required, no force beyond the 4 we already know, no separate physical laws operating in hidden dimensions. The identical copy does not need anything the standard model lacks. It needs only what the standard model, applied to an infinite flat universe, already predicts, that every finite configuration of matter must eventually recur. The logical chain is short. Flatness implies infinite space. Infinite space contains infinite Hubble volumes. Each Hubble volume can hold only a finite number of distinct quantum states. Infinity divided across a finite state space means every state appears infinitely many times. The nearest identical copy is the closest instance where that repetition produces a region indistinguishable from ours. Not roughly similar, identical, the same distribution of matter across 93 billion light-years, the same galaxies in the same positions. The same Earth, the same continents, the same evolutionary history, the same sequence of events that led to this moment. Somewhere beyond the horizon, at that incomprehensible remove, a narrator is speaking these words, not metaphorically, not as a thought experiment, as a direct consequence of the arithmetic. A student once asked Alan Guth, who helped develop inflation theory, and whose work on the early universe underpins much of this, whether an infinite flat universe implies infinite Earths. Guth closed his eyes for a moment before answering. When he opened them, he said, yes. And on one of them, you just asked a different question, and I gave a different answer. But here, we are having this conversation. That is the only version we will ever know. The rest are ghosts. Mathematically real ghosts. Mathematically real. That phrase does not soften the claim, it sharpens it. The ghosts are not hypothetical in the way that unicorns are hypothetical, conjured by imagination and unsupported by physics. They are hypothetical, the way a prime number you have never computed is hypothetical. It exists whether or not you have found it by the rules of the system. The other conversations, the other versions of this moment are real in the same sense that any mathematical truth is real. They are not accessible, they are not detectable. They are separated from us by a distance that cannot be traversed in any finite time, even at the speed of light, even in a universe that will expand forever. But the math that generates them is the same math that correctly predicted the CMB temperature, the large-scale structure of galaxies, and the flatness of space itself. Tegmark was asked directly in a 2012 interview whether he believes it. His answer, the math doesn't care what I believe. That is not a deflection. It is the most honest position available. The calculation does not require his belief, it does not require yours. If the inputs are correct and no observation currently contradicts them, the output stands. An infinite universe with finite information density produces infinite, identical copies of every configuration, including this one. Belief is irrelevant to the derivation. What makes this the most vertiginous claim in the film is precisely that it requires nothing new. Every other claim to strangeness in cosmology asks you to accept something unconfirmed. Dark energy as a field, inflation as a mechanism, a multiverse as a consequence of quantum fluctuations. The identical copy asks you to accept nothing but standard physics plus the number 0, the curvature parameter, flat to within measurement error. Follow the logic from there, and the copy is waiting at 10 to the 10 to the 28th meters, regardless of whether that distance disturbs you. This is the film's only time this specific claim will be made. Not because the math runs out, but because it only needs to land once. The number is already too large to revisit. It can only be encountered once, at full weight, and then carried. What comes next is the question the copy raises about the shape of the universe itself. Because if that shape is not infinite, if a small curvature hides in the Planck data's margin of error, then the copy disappears entirely, and the answer to what lies beyond changes without warning. The identical copy exists only if the universe is infinite, and whether the universe is infinite depends on a single number, its curvature. General relativity gives the universe 3 possible shapes, and they are not interchangeable. A positively curved universe bends back on itself in 4 dimensions, the way the surface of a sphere bends in 3. Travel far enough in any direction, and you return to your starting point. No edge, no boundary, no wall, but finite volume. A negatively curved universe opens outward like a saddle, expanding forever in all directions, infinite. And a flat universe, precisely zero curvature, also extends without limit, infinite in every direction, by a different geometric logic. The shape is not aesthetic, it is a verdict. It determines whether the universe has a finite amount of space to offer or an unlimited one. It determines whether the identical copy exists at all. The Planck satellite's final 2018 data release placed the curvature parameter omega k at 0.0007 with an uncertainty of plus or minus 0.0019. 0 is inside that error bar. The universe is consistent with being exactly flat to within the finest measurement cosmology has ever made, 0.2%. That is the precision of the answer. But notice what it does not say. It does not say the universe is definitely flat. It says a small, positive curvature, a universe that closes back on itself, finite and unbounded, is not yet ruled out. The difference between omega k equals 0 and omega k equals 0.001 is the difference between an infinite universe and a closed one, between the identical copy existing and the identical copy being meaningless. The data cannot currently resolve that gap. What a closed universe does to the question, what lies beyond, is strange enough to say directly. If the universe is positively curved and finite, the answer is not empty space. It is not a void. There is no beyond at all. The universe is everything, and everything curves back. Ask what lies beyond the surface of a sphere, and the question dissolves. There is no outside to the surface. A closed universe wraps the same way, in a dimension we cannot visualize. The question this entire film is built around becomes, under those circumstances, literally unanswerable, not because we lack the instruments, but because no answer exists. The geometry itself cancels the inquiry. That possibility is still open. The current instruments cannot push below a curvature threshold of roughly 0.5%. Below that line, the data goes quiet. Now consider the other side of the measurement. The universe is not merely consistent with flatness, it is suspiciously, improbably flat. In the early universe, curvature and the energy density of matter were in a delicate balance. A universe starting with even a tiny deviation from flatness would see that deviation amplified over time. A slightly closed universe would have collapsed back on itself long before galaxies formed. A slightly open one would have expanded into such thin dilution that matter could never have clumped into structure at all. The fact that we exist 13.8 billion years later in a universe that still reads as nearly flat to 4 decimal places means the initial conditions were tuned to extraordinary precision, not by a physicist, by whatever process set the universe in motion. This is the flatness paradox, and it is not resolved by pointing at the measurement. The measurement is the paradox. The universe should not be this flat, yet it is. The most widely accepted answer was proposed in the early 1980s. Cosmic inflation, a theory that posits a period of exponential expansion lasting a tiny fraction of a second immediately after the Big Bang, would have stretched whatever original curvature existed to near perfect flatness. The logic is geometric. Take any curved surface and expand it by a factor of 10 to the 26th or more, and the local patch visible to any observer becomes indistinguishable from flat. The same way the surface of the Earth appears flat from a human vantage point despite being a sphere, inflation does not eliminate curvature, it dilutes it past the point of detection. The theory is elegant, it is also at present entirely unconfirmed. The particle or field responsible for inflation, the inflaton, has never been detected. No experiment has found it. The signature inflation should leave on the cosmic microwave background a specific pattern of gravitational waves imprinted in the polarization of the CMB. Called primordial B-mode polarization, has not been found either. In 2014, the BICEP2 collaboration announced it had. The announcement was significant enough to generate widespread coverage and serious Nobel speculation. Within months, the Planck team demonstrated that the signal BICEP2 detected was consistent with dust in our own galaxy, not primordial gravitational waves. The announcement was retracted. The search continues. As of now, no observatory has detected direct evidence that inflation occurred. This does not mean inflation is wrong. It means inflation remains a hypothesis, the leading hypothesis, consistent with everything we observe, but unconfirmed by any smoking gun measurement. The flatness paradox demands some explanation. Inflation provides one, but the mechanism sits behind a wall we have not yet breached. In 2003, before BICEP2, before the Planck final release, the WMAP satellite produced its first-year results. The curvature constraint at the time was less precise than what Planck would later achieve, but the direction was clear. The universe was flat. Omega K sat near zero. Doctor. Lyman Page, one of the physicists who helped build WMAP's data pipeline and who spent years working toward that result, picked up the phone and called his mother in Ohio. He said, "Mom, the universe is flat." There was a pause. Then she asked, "Does that mean it goes on forever?" He said, "Yes." She said, "Then where does God put the throne?" Page laughed. He admitted later that he did not have an answer, not scientifically, not personally. He just sat with the phone in his hand, staring at a plot that read, "Your universe has no edge, no center, no end." That night, he walked outside and looked up at the sky. For the first time, he said, the word infinite felt not like a placeholder for something too large to picture, but like a fact, something the instruments had returned, something that now had to be lived with rather than merely contemplated. That is what the shape of the universe does when you follow it past the equation. It is not an abstract parameter. It is a verdict about whether beyond means anything, whether the identical copy is real or fictional, and whether the flatness we measure is a cosmic coincidence, an anthropic necessity, or evidence of a mechanism that left no other trace. The geometry decides everything, and the geometry is still not fully decided. Here is what the geometry section did not tell you. It handed you a number, omega K equals 0.0007, uncertainty plus or minus 0.0019, and called it the most precise geometric measurement ever made. It gave you flatness as near certainty, inflation as the leading explanation, and a model of the universe that, for all its open questions, seemed internally coherent. A structure with known load-bearing walls, even if some rooms were still locked. That structure has a crack in it, not a hairline. A fracture that has been widening for a decade, and that the community has not been able to close. There are two independent ways to measure how fast the universe is expanding. They should agree. They do not. The first method looks at the local universe, the universe as it exists now within a few 100 million light years. Astronomers use a chain of distance measurements called the cosmic distance ladder. At its base are Cepheid variable stars, stars that pulsate at rates precisely linked to their intrinsic brightness. Measure the pulsation period, calculate the true luminosity, compare it to how bright the star appears from Earth, and you get the distance. Then attach that distance scale to Type Ia supernovae stellar explosions, whose peak brightness is predictable enough to serve as standard candles across billions of light years. Build the ladder rung by rung, and you get a value for the Hubble constant, approximately 73 kilometers per second per megaparsec. For every megaparsec of distance between two objects, they recede from each other at 73 kilometers per second. The second method looks at the early universe. The cosmic microwave background, the oldest light we can detect, emitted 380,000 years after the Big Bang, carries acoustic imprints. Pressure waves frozen into the distribution of matter at that early moment. Feed those patterns into the standard cosmological model, run the equations forward 13.8 billion years, and the model predicts a Hubble constant of approximately 67 kilometers per second per megaparsec. 6 kilometers per second per megaparsec separates those two numbers. That gap sounds narrow. It is not. In physics, a 5 sigma discrepancy means the probability that random measurement error produced the difference is less than 1 in 3.5 million. It is the same threshold used to announce the discovery of the Higgs boson. When a result crosses 5 sigma, the field stops calling it a statistical fluctuation and starts calling it a signal. What kind of signal? It cannot yet say, but a signal. Both measurements have been stress tested. The Cepheid supernova ladder has been checked against independent distance indicators. The tip of the red giant branch, gravitational wave events, surface brightness fluctuations in nearby galaxies. They cluster around 73. The CMB analysis has been performed by independent teams with independent instruments, WMAP, then Planck, then ground-based arrays. They cluster around 67. Neither side is finding the error that would make the other side right. 3 explanations remain viable. First, one or both measurement chains carry an unknown systematic error, a miscalibration, a contaminating effect, something that has survived every check so far but is not yet understood. This is the most conservative possibility. It would mean the equations are fine and the measurements are the problem. Second, the standard model of cosmology lambda CDM is missing something in the early universe. Before the CMB was emitted, during those first 380,000 years, some physics occurred that the model does not capture. One candidate is an extra species of neutrino, a particle that would have altered the expansion rate during that window and shifted the CMB-derived Hubble constant upward. Another is early dark energy, a form of energy that was active in the early universe, diluted away before recombination, and left no other detectable trace. Either would require extending the particle physics standard model. Third, general relativity itself is incomplete, not wrong, but missing terms that matter at cosmological scales. a modification to gravity that deviates from Einstein's equations at very large distances or very long timescales, could shift the inferred expansion history. Each of these resolutions, if correct, changes the picture of the universe's composition. And a changed composition changes the age. It changes the curvature constraints. It changes every number that feeds into the extrapolations made earlier in this film. The distance to the identical copy, the size of the observable bubble, the geometry that determines whether the universe is finite or infinite. The Hubble tension is not a technical footnote. It is a fault line running under the foundation of everything that has been said about what lies beyond the horizon. DESI, the Dark Energy Spectroscopic Instrument in Arizona, is currently surveying tens of millions of galaxies, mapping the three-dimensional distribution of matter across cosmic time with higher precision than any previous spectroscopic survey. The Euclid Space Telescope, launched in 2023, is doing the same from orbit, targeting weak gravitational lensing and galaxy clustering to constrain the expansion history across billions of years. Both are designed in part to locate the crack, to determine whether the tension is in the data or in the theory. As of now, neither has closed it. What that means for this film specifically: every claim made about what lies beyond the horizon, the Tegmark number, the curvature constraints, the event horizon at 16 to 17 billion light-years was derived from equations calibrated against a universe we do not fully understand. The model that returned omega k equals 0.0007 is the same model that returns H0 equals 67 when the local universe says 73. We are using a ruler that gives different lengths depending on which end you hold. This does not mean the extrapolations are wrong. It means they are conditional. They are predictions made from the best available framework, and that framework has a demonstrated inconsistency that no one has resolved. The universe beyond the horizon may contain the identical copy or a closed finite geometry with no beyond at all, but the calculation pointing to either of those outcomes runs through a model that currently cannot account for the universe it can see. That is the specific nature of the unease. Not that the universe is large and strange. It has always been large and strange. But that the tools built to measure it are returning contradictory answers, and the contradiction is not shrinking. Every new telescope that sharpens the local value around 73, every new CMB analysis that holds the early universe value near 67, narrows the space available for a systematic error explanation and widens the space for something genuinely new. The standard model of cosmology may be correct everywhere it has been tested and still be wrong about the universe as a whole. That possibility is not hypothetical. It is, at 5 sigma, close to confirmed. The crack in the equations matters for a reason that goes beyond the equations themselves. Because while the cosmological model strains under the Hubble tension, something else is happening, something that requires no contested measurement to confirm, no unresolved debate to establish. It is happening right now at a rate that can be calculated, and it has been happening since the first galaxies formed. The horizon is not a fixed wall. It moves. Not toward us, that would at least imply a shrinking visible sky, something a future astronomer could detect by comparing sky surveys across millennia. The horizon moves outward in physical space, but the universe expands faster. The net effect is a boundary that, from our position, is consuming the observable domain. Galaxies that were once reachable by light, in principle, are crossing a threshold beyond which no signal they emit today will ever reach us. Based on the current expansion rate driven by dark energy at a Hubble constant, somewhere between 67 and 73 kilometers per second per megaparsec, depending on which end of the tension you trust, roughly one galaxy crosses that threshold every year and does not come back. One per year sounds manageable. It is not. That figure is an average across the full sky, and it compounds against a background of approximately 2 trillion galaxies in the observable universe. The galaxies vanishing now are the most distant ones, the faintest, the oldest, but the mechanism that takes them does not stop. It accelerates. Dark energy, whatever its nature, does not dilute as the universe expands. Matter thins out, radiation thins out, dark energy holds. The more space opens between galaxies, the more dark energy fills that space, and the faster the expansion drives the horizon outward against the finite speed of light. The process is self-reinforcing. The objects currently sitting at approximately 46 billion light-years, the edge of the observable universe right now, are already beyond the cosmic event horizon. That distinction matters. We can still detect their ancient light, photons emitted billions of years ago when those galaxies were much closer. But no photon those galaxies emit today will ever reach us. Their present state is permanently sealed from observation. We see their past. Their present is already gone from our universe in every practical and physical sense. This is not a prediction about the far future, it is a description of now. In 2016, a 12-year-old in Taipei named Marcus Chen won a regional science fair. His project was on the expansion of the universe. His presentation included a hand-drawn diagram of the event horizon advancing against the population of galaxies and a table of estimates. When his teacher asked him to explain what it meant, Marcus said, "Every year 100 billion stars cross the horizon and disappear. That's like emptying the Milky Way every week. We are losing the universe piece by piece, and nobody seems sad about it." His teacher did not have a response. He added one more sentence to his conclusion. "It's like we are in a boat and the shore is sinking. We can't row faster. The water itself is carrying it away." That image is physically precise. The shore is not receding because we are moving away from it. The water space itself is expanding, carrying the shore beyond the range of any possible signal. No improvement in telescope sensitivity, no increase in transmission power, no technological advancement of any kind addresses this. The loss is structural. It is written into the relationship between the speed of light, the age of the universe, and the behavior of dark energy. Dark energy was identified as a concept in 1998, when two independent teams, Saul Perlmutter's group and the High Z supernova search team led by Brian Schmidt and Adam Rees, discovered that distant Type Ia supernovae were dimmer than expected. They were farther away than the expansion rate at the time should have permitted. The universe was not just expanding, it was accelerating. Something was pushing space apart faster than gravity could counter. That something received the placeholder name, dark energy. It constitutes approximately 68% of the total energy density of the universe. Its identity remains unknown. Its equation of state, The relationship between its pressure and its energy density has been constrained, but not pinned down. Desi's early data suggested a possible variation in dark energy over cosmic time, though those results require further confirmation. What is not in dispute is the effect. The expansion accelerates, the event horizon advances, the galaxies fall behind. The number Marcus Chen cited, 100 billion stars per year, reflects the scale of what is being lost at the stellar level when you account for the typical stellar populations of the galaxies crossing the horizon. It is an order of magnitude figure, not a precision measurement. The precision measurement at the galaxy level is approximately 1 galaxy per year, based on current expansion parameters. Both numbers are ways of gesturing at the same process from different scales, and both are correct in the ways that matter. The loss is ongoing, it is permanent, and it is accelerating. One clarification that stops people when they first encounter this: the observable universe, the 9.3 billion light-year sphere established earlier, is not shrinking. Its physical diameter holds approximately steady, and in co-moving coordinates, the coordinates that expand with space, it barely changes at all over human timescales. What is shrinking is the fraction of the total universe contained within it. Every galaxy that crosses the event horizon reduces the domain of the knowable. The sphere stays the same size. The universe outside it grows. The ratio of what we can access to what exists is moving in one direction only. Marcus Chen did not attend the award ceremony. His mother said he was at home watching the simulation again. The simulation showed galaxies winking out at the edges, one by one, in real time. He had built it himself from publicly available expansion data and a fairly simple numerical model. He ran it on a school laptop. He watched it for hours. What he understood at 12, with no graduate training, with no access to the Planck dataset or the Hubble tension literature, was that the loss was not a future event requiring grief to be deferred. The loss was present tense. The loss was ongoing. And the question he could not answer, the one that sent him back to the simulation, was whether any record of the lost galaxies would survive long enough to matter. That question belongs to a later chapter. But the mechanism that generates it, dark energy, expanding space, a horizon that advances and never retreats, operates right now at 1 galaxy per year with no pause and no negotiation. The universe is not waiting for us to finish mapping it. Inflation was supposed to explain one thing: why the universe is so flat. In the early 1980s, Alan Guth at MIT and Andrei Linde, working independently in the Soviet Union, proposed that in the first fraction of a second after the Big Bang, somewhere around 10 to the minus 36 seconds space underwent a period of exponential expansion, so violent it made everything that came after look glacial. In an interval smaller than any we can directly measure, the observable universe inflated from a region smaller than a proton to something roughly the size of a marble. That is enough expansion to smooth out any initial curvature, to iron any wrinkles into the near-perfect flatness the Planck satellite would confirm 4 decades later. The theory worked. It explained the flatness. It explained the homogeneity, why regions of the universe separated by billions of light years have nearly identical temperatures. Even though they could never have been in causal contact without inflation having first connected them, It explained the slight density fluctuations in the CMB that seeded every galaxy we have ever mapped. The model passed test after test. Then someone asked, what happens when inflation stops? The answer was not clean. In Linde's version of the theory chaotic inflation, developed through the 1980s, the field driving inflation does not halt uniformly across all of space. Quantum fluctuations cause it to end in some regions while continuing in others. Where it continues explosively, generating new space at exponential rates, and those new regions are themselves subject to the same quantum fluctuations. So inflation continues in some of their subregions too. The process does not wind down. It proliferates eternally. While we sit inside one bubble where inflation ended 13.8 billion years ago and matter cooled into atoms and stars and eventually us, the inflating background keeps generating new bubbles, each one a separate universe. Each one potentially vast beyond any number that meant anything in previous sections of this script. Guth calls this eternal inflation. He considers it not a speculative add-on, but a nearly unavoidable consequence of the simplest, most observationally successful inflation models. The flatness and homogeneity of our universe, which inflation was built to explain those same explanations, carried to their logical conclusion, generate an infinite multiverse as a byproduct. It comes with the mathematics, whether you want it or not. Each bubble universe in this picture is causally isolated from every other. They do not communicate, they cannot. The space between them inflates faster than light. And inside each bubble, the physical constants need not be the same as ours. The mass of the electron, the strength of the electromagnetic force. The cosmological constant, the value that controls how strongly dark energy pushes space apart. In the framework of eternal inflation, these are not fixed outputs of a deep theory. They are environmental parameters, settled by accident when each bubble's inflation ended, the way a roulette ball settles into a slot. Our universe got the values it got. Other bubbles got other values, most of them presumably incompatible with the formation of atoms, let alone stars, let alone observers. This is where the anthropic principle enters, and where the theory begins to feel like it is pulling a card from its sleeve. The question the multiverse answers is one that has bothered physicists for decades. Why are the constants of nature so precisely calibrated for the existence of complex structures? The cosmological constant, for example, is observed to be extraordinarily small. Small enough that dark energy does not rip atoms apart. Small enough that gravity can assemble galaxies. Calculations from quantum field theory suggest it should be vastly larger, perhaps by a factor of 10 to the 120. The discrepancy between the predicted and observed value is the largest unexplained number in physics. If the cosmological constant were even slightly larger than it is, no galaxies would have formed. The universe would have expanded too quickly for matter to clump. The multiverse's answer: there is no fine-tuning. There are simply an enormous number of bubbles with different values of the cosmological constant, and we necessarily find ourselves in one of the rare bubbles where the value permits structure to exist. We could not be anywhere else. The constants appear designed because the only universe we could have evolved in to ask this question is one where the numbers work. That is the anthropic principle. Steven Weinberg used a version of this argument in 1987 to predict, before the discovery of dark energy, that the cosmological constant should be small but non-zero. 11 years later, it was confirmed to be exactly that. Some physicists regard this as the strongest possible evidence that the multiverse is real. The prediction worked. Paul Steinhardt is not one of them. Steinhardt, one of the early architects of inflation, has spent years arguing that the theory has collapsed under its own success. He and Anna Ijaz at Columbia and then the Max Planck Institute for Gravitational Physics laid out the case systematically. If eternal inflation is true, then every possible observation is consistent with the theory. A universe with our constants, consistent. A universe with wildly different constants, also consistent. It exists in another bubble. Any CMB measurement, any curvature result, any Hubble constant, all of it is consistent, because somewhere in the infinite multiverse, all values are realized. A theory that accommodates every possible observation rules out none of them. It makes no testable predictions. And a theory that makes no testable predictions is not science. It is a framework so flexible it has become unfalsifiable by construction. Steinhardt's position is not that eternal inflation is wrong. His position is that we cannot know whether it is wrong. That distinction matters enormously. Linde and Guth push back. Falsifiability, they argue, is not the only standard a theory must meet. The logical structure of eternal inflation follows from equations that have already been tested, the same equations that predicted the CMB fluctuations we measure, the same equations that predicted the flatness Planck confirmed. If you accept the theory where it is testable, you are accepting the machinery that generates eternal inflation. Rejecting the multiverse then requires rejecting parts of the framework that have already passed observational tests, which introduces inconsistencies of its own. You cannot take the predictions you like and leave the rest. Neither side is bluffing. Both arguments are serious. The debate has been active for decades and shows no sign of resolution. What the multiverse is not in this script or in any honest accounting is a confirmed entity. It appears here as a consequence of inflation, a logical output of the best tested theory for why the universe looks the way it does. Whether that consequence is a physical reality or a mathematical artifact is precisely what no one can determine from inside a single bubble. We are in one. We can measure its properties. We cannot see the others, reach them, or send a signal to them. The bubble wall where our inflation ended and space began cooling into matter is not a place any instrument will ever reach. The anthropic principle offers comfort of a sort, an explanation for why the numbers work, a reason to expect them to work even without a designer. But the comfort requires accepting that most of the universe's structure, its constants, its particle masses, its fundamental forces, are not deep necessities, but lucky accidents. That the electron has the mass, it does not because physics demanded it, but because we happen to land in a bubble where that value permits chemistry to exist. That is either the only logical conclusion available, or it is the most sophisticated evasion in the history of science. The answer depends on a question no measurement from inside this bubble can ever settle. The multiverse argument has a problem, not with the physics, with the counting. If eternal inflation is true, if the universe is genuinely infinite and has been generating new regions of space for an arbitrarily long time, then the quantum vacuum is not empty. It fluctuates, constantly, everywhere, at every scale. And given infinite time and infinite space, Those fluctuations are not constrained to producing particles or atoms or galaxies. They can produce anything that is not physically prohibited, including minds. This is not a metaphor. It follows from the same statistical mechanics that governs every thermodynamic system. Ludwig Boltzmann understood it in the 19th century, applying it to the heat death of the universe. In a system of sufficient age and size, random fluctuations will occasionally assemble low entropy configurations, ordered structures out of chaos. Boltzmann was thinking about galaxies spontaneously forming in an otherwise dead universe. Later, physicists followed the logic further. If a fluctuation can assemble a galaxy, it can assemble a star. If it can assemble a star, it can assemble a planet. If it can assemble a planet, it can assemble a brain, not just a brain. A functional mind, complete with sensory data, apparent memories, the felt certainty of a continuous past. A mind that believes it evolved on a planet, watched stars through telescopes, learned physics, and is now watching a documentary about the edge of the observable universe. A mind with false memories of a history that never happened, embedded in a cosmos that does not exist, assembled in a single thermodynamic accident and dissolving moments later back into the void. These are called Boltzmann brains, and in an infinite, eternal universe, they outnumber us. Not slightly, not marginally. The ratio is catastrophic. An ordinary observer like you required 13.8 billion years of cosmic history. Inflation had to smooth the initial conditions. Matter had to clump under gravity. Stars had to forge heavy elements and die. Second-generation stellar systems had to form with the right chemistry. Life had to emerge and sustain itself across geological timescales. And evolution had to produce the specific neural architecture you are using to process this sentence. The probability of all that, given the physics, is extremely small. But the probability of a quantum fluctuation spontaneously assembling the specific brain state you occupy right now, without any of that history, without the planet, without the galaxy, is smaller still. The question is, which is more probable, the entire causal chain or just the end point? In an infinite universe, both happen infinitely often. The question is their ratio, and the ratio, under the simplest assumptions, is not close. For every one observer that evolved the way you did, there should be an enormous number of observers that simply fluctuated into existence, complete with counterfeit memories of having evolved. If you were selected randomly from all observers in an infinite eternal universe, the odds that you are a Boltzmann brain are not trivial, they are overwhelming. The most probable version of you, statistically, is a fluctuation, not a product of cosmic history at all. So, why are you not one of them? You feel continuous. You remember yesterday. You have a past that you trust. But a Boltzmann brain would feel exactly the same way. Its false memories would be indistinguishable from your real ones. The sensation of having a history proves nothing about whether the history is real. And this is not a philosophical sleight of hand. It is a concrete statistical challenge to every model that combines infinity with eternal fluctuations. The fact that we observe an orderly universe becomes, under this logic, suspicious. We see a cosmos with a coherent 13.8 billion year history. The CMB matches the predictions of the Big Bang to extraordinary precision. The large-scale structure of matter exactly follows from the initial conditions we have measured. Everything is consistent, causal, and organized. That is exactly what a real evolved observer should see. It is also exactly what a Boltzmann brain's false memories would contain. Our own experience of order is not a proof of order. It is data that requires explanation. And here the problem bites the infinite models hardest. The orderly universe we observe is evidence not against the Big Bang, which is extremely well supported, but against the simplest infinite eternal frameworks that generate vast numbers of fluctuating minds. If those frameworks are correct, observers like us should be vanishingly rare. Yet we observe ourselves to be observers like us. That asymmetry demands a reckoning. Two responses exist. The first, treat the Boltzmann brain conclusion as a reductio ad absurdum. If a model predicts that most observers are disembodied fluctuations, and we are not disembodied fluctuations, then something in the model is wrong. Either our assumptions about infinity are incorrect, or our understanding of thermodynamics in an eternal universe is incomplete, or the probability calculus we are using does not apply to infinite spaces in the way we think it does. The Boltzmann brain is then not a feature of reality, but a signal that the theory has broken down, a pointer at a crack in the foundation we have not yet located. The second, accept that we do not know how to correctly count observers in an infinite space. The problem of assigning probabilities across infinite sets the measure problem in cosmology is genuinely unsolved. There is no agreed-upon way to say, in an infinite multiverse, what fraction of observers are Boltzmann brains versus ordinary ones. Every proposed measure generates different answers, some of which avoid the Boltzmann brain problem and some of which make it worse. Without a resolved measure, the statistical argument cannot be completed. The counting is broken, not necessarily the universe. Neither response is satisfying. Both are serious. The debate has run for decades among physicists who are not confused about the mathematics, and no one has dissolved the problem cleanly. It sits in the literature, unresolved, attached to every infinite universe model like a warning label no one has managed to remove. Dr. Rebecca Bowman was at a supercomputer screen watching a simulation of dark energy drive galaxies across the horizon, one by one, winked out of the observable universe, permanent and irreversible. She stopped the simulation before it finished. "The horizon isn't a wall," she said. "It's a door that only opens one way away from us." She was talking about galaxies. But the door she described opens inward too. The cosmic event horizon erases what lies outside. The Boltzmann brain problem questions what lies inside specifically, whether the mind doing the observing is what it believes itself to be. Both problems trace back to the same architecture, an infinite universe fluctuating eternally, indifferent to the distinction between real histories and manufactured ones. You cannot step outside your own cognition to verify it. The instruments are inside the system they are trying to measure. That is the door, and it only opens one way. Here is what no upgrade to our instruments will change. The universe beyond the horizon is causally disconnected from us. That phrase sounds technical. What it means is absolute. No signal, no photon, no gravitational wave, no particle of any description can ever arrive from beyond that boundary, not because our receivers are too small or our telescopes too few, But because the structure of space and time prohibits it, the expansion of space between here and those regions is carrying them away faster than any signal travelling at light speed could ever bridge. This is not an engineering problem. It is a verdict written into the geometry of the universe itself, and no future civilization, however advanced, will overturn it. Every instrument we have ever built, every satellite we have ever launched, every antenna array we have ever assembled, all of it operates inside the bubble. It always will. The question then is how much the bubble can tell us about what lies beyond it. The answer is less than we would like and more than nothing. The cosmic microwave background is the sharpest tool we have, and it is also the last one. That faint thermal afterglow, measured to high precision by COBE in 1992, refined by WMAP through the 2000s, and pinned down with the highest accuracy ever achieved by the Planck satellite in 2018, is the direct physical imprint of the universe at 380,000 years old. It is not an image of a distant object. It is the wall of the observable bubble itself, the moment when the early universe first became transparent and released its light in every direction. Nothing from an earlier time reaches us directly. Nothing from beyond that surface reaches us at all. Everything we know about the geometry of space, the curvature of the universe, the density of matter and dark energy, it was extracted from that signal. The flatness result, omega k equals 0.0007 plus or minus 0.0019, came from the CMB. So did the age of the universe, 13.8 billion years. So did the composition ratios that underlie every extrapolation we have made in this film. Beyond the CMB, there is no direct evidence, only inference drawn from what landed on this side of the wall. That inference has limits. Currently, curvature cannot be ruled out below the 0.5% level. The Planck 2018 result is consistent with exact flatness, but a small positive curvature, a universe curved back on itself like the surface of a sphere in a higher dimension, finite and unbounded remains within the allowed range. If the universe is closed at a curvature just below the detection threshold, then the question of what lies beyond the horizon has a specific answer. Nothing. Not empty space. No beyond at all. The universe wraps back on itself, finite in volume, and the word beyond becomes geometrically meaningless. We cannot rule that out. Right now, 4 experiments are working to push that ceiling lower. The South Pole Telescope and the Atacama Cosmology Telescope are measuring CMB polarization at higher resolution than Planck could achieve. DESI, the Dark Energy Spectroscopic Instrument in Arizona, is mapping the 3-dimensional distribution of 40 million galaxies to constrain how the universe has expanded over time. The Euclid Space Telescope, launched in 2023, is performing a wide-field survey of galaxy shapes and clustering across more than a third of the sky, targeting the geometry of large-scale structure. These are serious instruments doing serious work, but none of them will breach the ceiling. They will narrow the allowed range of curvature. They will not close it to zero. The instruments that would definitively determine whether the universe is infinite or merely vast instruments that could, in principle, detect the topological signature of a finite universe in the CMB, the faint ghost of a repeated pattern that would confirm the space wraps do not exist. The signals may not be extractable from the noise of the foreground sky. Some configurations of a closed universe would leave a pattern in the CMB too subtle for any physically realizable telescope to isolate. This is not pessimism. It is the measurement physics. And so every claim made about what lies beyond the horizon, the identical copy at 10, 10, 28 meters, eternal inflation, the multiverse of bubble universes rests on a foundation that cannot be directly tested from inside a single bubble. Those claims follow logically from the assumption that the laws of physics operating here apply uniformly out there, past the boundary, in regions we will never reach. That is a reasonable assumption. It is consistent with everything we have measured. It is the simplest position available. It is also unverifiable, not eventually, now and permanently. The Hubble tension adds a sharper edge to that point. Within the observable universe, entirely within our own bubble, inside the region where we have direct data, two independent methods of measuring the expansion rate disagree at 5 sigma confidence. The local measurement and the CMB-based measurement return different numbers, and the gap has not narrowed as precision has improved. If our standard equations cannot fully account for the expansion history of the universe we can see, then using those same equations to characterize the universe we cannot see is an act of extrapolation, resting on a model we know is incomplete. The foundation may be structurally sound. It may have a hairline fracture running through it. From inside the bubble, we cannot tell which. Dr. Rebecca Bowman put it plainly. Standing in front of data she could not explain away, the horizon is a door that only opens one way. From a purely empirical standpoint, the beyond horizon universe is not a region with incomplete data. It is a region with no data, structurally, permanently, by the architecture of space-time itself. The CMB is the last wall, and we are pressed against it with every instrument we have. What lies on the other side is not unknowable because we haven't looked hard enough. It is unknowable because looking, in any physical sense, is impossible. What remains is reasoning following the logic of confirmed theories past the boundary they were built inside. Whether that constitutes knowledge or something else entirely is the question this film now has to answer. Here is the question that has been building since the first number appeared on screen. Not what lies beyond the horizon, whether the question belongs to physics at all. George Ellis is one of the most respected theoretical cosmologists alive. He co-authored the foundational textbook on space-time structure with Stephen Hawking. He has spent decades thinking carefully about what science can and cannot claim. And his position on theories of the unobservable universe is unambiguous. A claim that cannot even in principle be tested by any possible observation is not a scientific claim, it is metaphysics. The equations may be rigorous, the reasoning may be internally consistent, none of that changes what it is. Dress metaphysics in the notation of general relativity, and it is still metaphysics. Ellis is not dismissing the multiverse or the identical copy because they seem outlandish. He is applying the oldest standard in empirical science. Karl Popper formalized it. A theory is scientific if and only if it can, in principle, be falsified. A theory that accommodates every possible observation because it predicts that all possible observations occur somewhere in an infinite space is not a theory. It is a framework so permissive that it is immune to evidence. And immunity to evidence is not a feature of good science. It is the definition of its absence. The opposing position is held with equal seriousness. Max Tegmark argues that restricting cosmology to what instruments can directly confirm would require us to abandon the logical consequences of theories that have been tested with extraordinary precision inside the observable bubble. General relativity has passed every test to which it has been subjected. Quantum mechanics underlies the most accurate predictions in the history of physics. If those frameworks are correct here, their implications do not stop at the horizon. The horizon is not a physical boundary in space, it is a limit of information. The laws of physics do not care where our detectors are. Alan Guth makes the same point from the inflation side. The mechanism that explains the CMB's flatness and its temperature uniformity across regions that should never have been in causal contact, eternal inflation almost inevitably generates bubble universes beyond our reach. You cannot accept the explanation and reject the consequence. If the model is right within the bubble, and the evidence says it is, then the multiverse is not speculation appended to the theory. It is embedded in it. So the divide is not between rigorous physicists and loose thinkers. It is between two legitimate positions on what science is for. And Tegmark asked directly whether he believes the identical copy at 10-10-28 meters actually exists, did not hedge. He said, "The math doesn't care what I believe." That answer was not a deflection. It was a precise statement about the relationship between a physical theory and the convictions of the person holding it. He was saying, I derive this prediction from assumptions the data support. Whether I find it comfortable is irrelevant to whether it is true. The math runs forward regardless of what any physicist thinks of the destination. That is either the purest form of scientific integrity or a description of how physics loses its footing. Depending on which side of the divide you stand on, it is both. Here is the actual danger Ellis is pointing to. If cosmology extends its claims beyond what any observation could ever falsify, it undergoes a structural transformation. It stops being a discipline constrained by evidence and becomes a discipline constrained only by mathematical self-consistency. Mathematical self-consistency is a weak constraint. Many things are internally consistent that are not true. Ptolemy's epicycles were internally consistent. A theory that can predict anything because an infinite multiverse contains every possible outcome somewhere predicts nothing about this universe, this observation, this measurement. It becomes a closed loop. The stakes of that transformation are not merely academic. If the leading framework in cosmology is unfalsifiable, then the resources, careers, and intellectual effort poured into developing it are not advancing empirical knowledge. They are advancing a very sophisticated story about what might be true. That is not a small distinction, but the alternative Ellis offers carries its own cost. If cosmology restricts itself strictly to testable claims, it must stop at the horizon. It must say, we can measure the curvature of the observable bubble, constrain the expansion rate, catalogue the large-scale structure, and beyond that wall we are silent. That is an honest position. It is also one that severs the discipline from the logical consequences of its own confirmed theories. You would be in the position of trusting general relativity enough to use it for GPS satellites and gravitational wave detection. but refusing to follow its equations into the regions they also describe. That tension has no clean resolution. The line between rigorous prediction and unfalsifiable myth is not clearly drawn in current cosmology. The practitioners who have thought about it longest disagree on where it runs. No consensus exists, not even a dominant position. This is an open fracture in the foundations of the field, and it has been open for decades. The promise made at the start of this film was that we would reach this question. We have reached it. If we can reason our way past the horizon, following the logic of equations that work inside the bubble, tracing them outward into a region permanently sealed from observation, what exactly are we doing? Is it science? Is it rigorous extrapolation that carries the authority of tested physics? Or is it, in Ellis's framing, a creation myth with better mathematics? The film cannot answer that question. Not because the answer is being withheld, because the answer does not exist yet. The people who spend their lives on this problem have not resolved it. The institutions that fund the research have not settled it. The journals that publish the papers contain both positions, side by side, unreconciled. What lies beyond the horizon may be more of the same, extending forever. It may be a finite universe curling back on itself with no beyond at all. It may be an infinite field of bubble universes, each sealed from the others, each running different physics. These are not equivalent claims. They cannot all be true. But from inside this bubble, pressed against the CMB wall with the best instruments our civilization has built, no measurement will tell us which one it is. The horizon does not ask what you believe. It simply holds, consider what we are about to lose. Not eventually, not in some abstract epoch beyond reckoning. Now, this year, while you are watching this, the horizon is not a static line, it is a process. Every year, galaxies that were once in principle reachable by light recede past the point from which any signal could ever return. They do not vanish from the sky tonight. Their ancient light keeps arriving, the last installments of a transmission already cut off at the source. But their present state, whatever is happening in those galaxies right now, is already sealed away. Not by distance alone, by physics, by the expansion of space itself, which does not slow at the boundary of our attention. This is what a 12-year-old in Taipei understood, that most people never stop to confront. Marcus Chen won a science fair in 2016 with a project on cosmic expansion. He stood in front of a simulation and said what the data actually shows. Every year, 100 billion stars cross the horizon and disappear. That is the equivalent of emptying the entire Milky Way every week, permanently, with no recovery possible. His teacher had no response. Marcus added something that landed harder than most published papers on the subject. It is like being in a boat while the shore is sinking. Not drifting away, sinking. You cannot row faster because the water itself is carrying it down. He did not attend the award ceremony. His mother said he was at home watching the simulation again. The mechanism behind his grief is simple and irreversible. Dark energy, the force driving the accelerating expansion of space, does not weaken as regions empty, it grows. The emptier a volume of space becomes, the stronger the outward push. This means the loss compounds. The rate at which galaxies cross the event horizon is not constant, it accelerates. What begins as one galaxy per year lost to the permanent dark becomes, on cosmological timescales, a cascade. Follow that cascade far enough forward, and the picture becomes something no science fiction writer has fully reckoned with. In the far future, not millions of years but billions, stretching toward trillions, any observer anywhere in the universe will look out and see nothing beyond their local cluster of galaxies. Not a thin scattering of distant light. Nothing. The surrounding universe will not appear to have been emptied. It will appear to have always been empty, because the evidence of what was once there will be gone. Not archived somewhere, inaccessible. Gone. Carried past a horizon that moved faster than the light that could have carried testimony back. The cosmic microwave background will be the first great casualty. Right now, the CMB is the single most important piece of observational evidence in all of cosmology. It is the thermal afterglow of the Big Bang photons that decoupled from matter 380,000 years after the universe began, carrying a precise blackbody spectrum imprinted with the earliest density fluctuations in the history of space. Every major result in this film rests on it. The flatness measurement, the age of the universe. The composition ratios, the Hubble constant on one side of the tension, all of it derives from that relic radiation. Expansion will destroy it, not suddenly. Over enormous spans of time, the CMB will cool and redshift its wavelengths, stretched by the growth of space itself, until it falls below the thermal noise of empty space. It will become indistinguishable from nothing. A future civilization pointing their best instruments at the sky will find no trace of it. Not a degraded signal. Not a faint remnant requiring better technology to detect. Nothing that physics, applied honestly, would distinguish from the quiet of a universe that had no beginning. Without the CMB, the chain of inference collapses. Future scientists will have no direct evidence that galaxies once filled the observable sky. No evidence that the universe was ever expanding. No grounds from observation alone to conclude there was a Big Bang at all. The Hubble diagrams, the redshift surveys, the large-scale structure maps these measurements depend on light that has already reached us, light that is arriving now and in the coming centuries. After a certain threshold, that light will have finished its crossing. The universe will have nothing more to send. They will inherit silence. And silence, to a scientist with no other reference, looks exactly like the natural state of things. This is not a failure of curiosity or ambition on their part. It is an epistemological inheritance forced on them by physics. A civilization arising in that era, with instruments as sensitive as any we can conceive, will look out at their local cluster, the Milky Way, Andromeda, the gravitationally bound remnants of what we call the local group, and see a static island of stars surrounded by an empty and apparently eternal void. The universe will seem to have no history, because the history will have departed. They might build theories. They might reason carefully from what they have. But the evidence that would confirm those theories, the galactic redshifts, the CMB anisotropies, the distribution of matter across 1 billion light years, will be gone, not hidden. Physics does not retain what expansion has erased. Today is different. This epoch is different. The universe is young enough that the light from its early structure has had time to reach us, and old enough that we have built instruments capable of reading it. The Planck satellite captured a map of the CMB with sufficient precision to constrain the curvature of the universe to within 0.2%. The Hubble Space Telescope and its successors catalogued the recession velocities of galaxies across billions of light years. The James Webb Space Telescope reached back to within 300 million years of the Big Bang and pulled a ghost image from the void. All of this was possible only because we exist in a specific, narrow, unrepeatable window between the universe being too hot and opaque to observe and too empty and cold to contain evidence worth finding. That window is closing. It has been closing since the first galaxy crossed the horizon. Everything we have mapped, catalogued, and understood about the large-scale universe, the full architecture of the cosmic web, the composition ratios of dark matter and dark energy, the measured age of 13.8 billion years, the case for inflation, the Hubble tension, the geometry of space, this entire edifice of knowledge is contingent. It rests not on permanent features of reality, but on the accident of timing. We were born into the right billion years. Future observers will have to take our records on faith. If the records survive in whatever form civilization manages to preserve them across cosmological time, a future scientist might read that the sky was once full of galaxies. Might read that a bath of ancient photons proved the universe had a beginning. Might read that two measurements of expansion disagreed by 6 kilometers per second per megaparsec, and that this mattered enormously to the people who made them. They will have no way to verify any of it. The observations cannot be repeated. The light will not come again. Marcus Chen was 12 years old when he named this clearly. We are losing the universe piece by piece, and nobody seems sad about it. The full weight of that is available now, after everything this film has traced the horizon as a time limit. The identical copies sealed forever beyond reach, the Boltzmann brains that question our own statistical standing, the cracked foundation of our expansion measurements, the Ellis-Tegmark divide over whether any of our extrapolations constitute science at all. All of it happens inside a bubble that is not just spatially bounded, but temporally bounded. The observable universe is a temporary window, and we are the brief civilization that happened to open its eyes while there was still enough light to see by. The silence that follows will not know what it lost. What we are left with, after everything, the flatness measurement, the ghost galaxy, the cracking foundation of the Hubble tension, the Boltzmann brains, the Ellis-Tegmark impasse is a fact about timing, not a metaphor about timing, a literal, datable, measurable fact. The evidence exists now. It will not always exist. And we are the civilization that happened to be present while it still did. That is not consolation. It is a responsibility. Consider what it means to catch the universe in the act. The Planck satellite, in its final 2018 data release, returned a curvature parameter of 0.0007 plus or minus 0.0019. That number was possible to measure because the cosmic microwave background was still detectable, still arriving, still carrying the thermal imprint of matter and radiation decoupling 380,000 years after the Big Bang. The James Webb Space Telescope captured light that left a galaxy when the universe was 300 million years old. Light that crossed 13.5 billion years of expanding space to hit a mirror we built for exactly this: purpose at exactly this moment. The Hubble diagrams that revealed accelerating expansion in 1998 were built from supernovae in galaxies whose recession velocities are measurable now, while those galaxies are still within reach of observation. None of this will be available to a civilization born 10 trillion years from now. Not degraded, not difficult, gone. A civilization arising in that era will inherit what physics leaves after expansion finishes its work. A static, local cluster, surrounded by a void that appears to have no history. They will have no way from observation alone to recover what we mapped. The records, if any survive across that span, will be the only testimony. And testimony without the capacity to verify it against the sky is a different kind of knowledge. It is what we call faith, or history, or mythology, depending on how much distance has accumulated between the claim and the evidence. This is not a sentimental point. It has a precise structure. Every major result in modern cosmology depends on light that has already arrived or is arriving now. The flatness measurement, the age of the universe. The composition ratios: 5% ordinary matter, 27% dark matter, 68% dark energy. The existence of the cosmic web. The case for inflation. The Hubble tension itself, which cannot even be resolved without access to both the CMB signal and the local distance ladder. All of it is built from photons that left their sources billions of years ago and reached us in this specific narrow epoch. That epoch is not a permanent feature of the universe. It is an accident of when we arrived. Alan Guth said it at the end of a lecture to a student who had asked the right question. He closed his eyes for a moment, then opened them. Here, we are having this conversation. That is the only version we will ever know. The rest are ghosts. Mathematically, real ghosts. He was talking about identical copies beyond the horizon, but the same sentence applies to the evidence itself. The CMB map that Lyman Page helped build, the redshift surveys that traced galaxies across billions of light years, the JWST image of JADESGSZ 130, these are the version we will ever know. A civilization 10 trillion years forward will not have them. The photons will be gone. The horizon will have consumed the sources. The ghosts will have dispersed. So, what do we owe that future? The answer is not obvious. Dr. Rebecca Bowman watched a simulation of dark energy erasing galaxies from the edge of the observable universe and stopped it halfway through. She said later that she could not breathe, not because the simulation was dramatic, but because she understood what it represented. Those galaxies are real. There are civilizations there, maybe. And we will never, ever know them. Not because we aren't trying, because the universe itself has said, too far. The horizon is not a failure of ambition. That is the specific thing Bowman identified. It is not that our telescopes are too small, or our rockets too slow, or our funding too limited. The universe has issued a structural verdict. The expansion of space is not a problem that better engineering will solve. It is a feature of reality that cannot be negotiated. And yet the reasoning continues. This is what the film has traced, not a series of discoveries leading to an answer, but a series of discoveries leading to a sharper understanding of the question. The Planck curvature result did not answer what lies beyond the horizon. It made the question mandatory. The Tegmark calculation did not prove the identical copy exists. It showed that taking infinity seriously forces the conclusion. The Boltzmann brain problem did not resolve the debate about our own statistical standing. It sharpened the terms. What lies beyond the horizon may never be seen. That is not a temporary condition awaiting better instruments. It is written into the causal structure of space and time. No signal from beyond the event horizon will ever reach us. No observation will confirm or refute what the mathematics implies. The question will remain open not because physics has not tried, but because physics itself has traced the boundary and found its seal. The act of reasoning past that boundary anyway, of following general relativity and quantum mechanics to their logical ends, of calculating distances that exist only in mathematics, of asking whether the question belongs to science or to something older, that act is among the most significant things a civilization can do. Not because it produces answers, because it maps the shape of what cannot be known, and that shape is itself information. The record exists. Right now, in this epoch, the measurements are real and verifiable and open to scrutiny. The CMB maps are archived, the redshift catalogues are published, the JWST data is in the public domain. Any astronomer alive today can check the numbers. Future scientists may not be able to replicate them, but we can confirm them now, in the only window when confirmation is possible. That confirmation is the legacy, not the answers, the verified record of what the universe looked like when we could still see it whole. We caught it expanding. We measured its age. We traced its geometry to within 0.1%. We reached back 13.5 billion years and photographed a galaxy that no longer exists. We found a tension in our own equations that we have not yet resolved, which means we also recorded our own uncertainty honestly, which is the most that science has ever been able to promise. The horizon does not end the story. It marks the boundary of the version we can tell. And this is the version we will ever know. Not a partial version awaiting completion, not a draft, the one that exists in this narrow, unrepeatable window between the universe being too young to see and too empty to remember. The evidence is here. The instruments are running. The measurements are real. The record stands, for now, in the only epoch when it could have been made.